Okay, welcome to BME 271 Lecture 8. In this lecture we are going to be introducing impedance representations of basic circuit elements. We're going to be doing a complex arithmetic review because these two are going to be tied together essentially. Impedance representations are going to involve complex numbers. And then we're going to talk about passive filters. So these are impedance representations, and the fact that we know how to and our ability to manipulate complex numbers is going to allow us to analyze frequency-selective filters. And by passive filters, I mean filters made up entirely of resistors, capacitors, and inductors. So first, impedances. So what we're going to do is we will represent the impedance of resistors, capacitors, and inductors as functions of frequency. That's fundamentally what an impedance representation does. So an impedance of a resistor is simply R, right? We know that resistance is not dependent on frequency or any time domain characteristics of a signal, so it's constant. It's independent of frequency. So in this case we have that Z equals R for a resistor. On the other hand, a capacitor impedance is given by 1 divided by j omega C. So j here is the square root of minus 1, which we'll talk about a little bit more in a couple slides. Omega is the frequency in radians per second, and C is the capacitance in farads. And so you can see that because it's inversely proportional to omega, the impedance of a capacitor decreases with increasing frequency. And the third one is an inductor. An inductor's impedance is given by j omega times capital L. So j again is the square root of minus 1, omega is the frequency in radians per second, and L is the inductance in henries. And because this is proportional to omega, directly proportional to omega, it's going to increase with increasing frequency. So one of the nice things about impedance representations of circuit elements is that they let you treat all your elements like resistors. So for example, let's say that we have the following circuit. Let's say that we have a parallel combination of a resistor and a capacitor. And so then the resistor has resistance R and the capacitor has C. So if we represent their impedances, if we represent them as a set of impedances, then we can combine them just like their resistors. And we can say that we can use the parallel combination equation for resistors and say that 1 over Z equivalent, if we call Z equivalent if we say that this parallel combination is equivalent to 1 impedance, then that impedance is given by, 1 over that impedance is given by 1 over R plus 1 over j omega C. And we can simplify this out, and we can see that Z equivalent is equal to R over 1 plus j omega times R times C. Okay, so one of the nice things about impedances is that we can take some parallel combination of arbitrary elements, and we can represent them as a single one. We can always treat them as resistors, right? We can always do the math as though we're doing the math of combining them with resistors. So we've seen now that we're going to be dealing with complex numbers when we're manipulating impedances. So I think it's appropriate at this point to give you a little review of complex arithmetic. So first, a little history on the application of complex arithmetic to analyzing circuits. So this guy Charles Steinmetz, he used to work at GE, I believe. Around 1890, he was working on AC circuits, right? So circuits to process time-varying signals. And he was getting tired of solving these time-domain circuit equations, right, involving all the derivatives with respect to time and doing all the calculus involved in that. And what he recognized, though, was that if he's inputting sinusoidal signals of one frequency or some small set of frequencies into his circuits and looking at the effect of the circuit on those signals, he could really describe that effect fully by characterizing what it did to the magnitude of each sinusoidal signal and the phase of each sinusoidal signal. And what he recognized was that a capacitor's voltage this should actually be lags its current, I have this swapped, by 90 degrees, and an inductor's voltage leads its current. Sorry, an inductor's voltage leads its current, on the other hand, by 90 degrees. And so you basically needed to distinguish between these plus 90 and minus 90 phase shifts. You need a number whose inverse is its negative, right? So mathematically we would write that as, if we have a number a whose inverse is its negative, then this number should satisfy 1 over a equals minus a. And we can get that by using the square root of minus 1. So let's show that. So the square root of minus 1 inverse is equal to 1 over square root of minus 1, obviously. So it's 1 over square root of minus 1 times square root of minus 1 divided by square root of minus 1, which is equal to square root of minus 1 over minus 1, right? Because the two square root of minus 1s cancel out, and we get minus 1 from those, which of course is just equal to minus square root of minus 1. So this is a number whose inverse is its negative. So complex numbers, though, in general are going to have both a real part and an imaginary part. So let's denote a complex number as some a plus bj. So where j is equal to the square root of minus 1, a is the real part, and b is the imaginary part. Now, just like Steinmetz, what we really care about is the effect of our circuits on the magnitude and the phase of a signal. And the magnitude, given a representation a plus bj, is equal to square root of a squared plus b squared. And the phase of a signal is given by the inverse tangent, the arctangent, right? The phase of a complex number is given by arctan, the inverse tangent, of the ratio of the imaginary part to the real part. Okay? Okay, so what happens if we take two complex numbers and we divide them by each other? So here we have a complex number a plus bj and a complex number c plus dj, and then we're going to divide them by each other, and we want to know what happens to their magnitude, to the magnitude and phase of that of the division. Okay, so the magnitude, we know that what the magnitude of each of these numbers is on their own, and so the ratio of the two is just the ratio of the magnitudes. So what we're going to end up with is a squared plus b squared divided by c squared plus d squared square root. Right. So as you might imagine, it's just the ratio of their own magnitudes. The phase is a little bit funnier though, because you have the phase of their ratio is given by the difference of their phases divided by tan inverse of d over c. So in both cases, it's the imaginary part divided by the real part, and then we take the arctangent of that, and if you have a ratio of two numbers, then you subtract the phase of the guy in the denominator. So note here that all of these coefficients, a, b, c, and d, can in general be functions of frequency, right, of temporal frequency omega. And indeed, that's what we're going to see when we actually start constructing filters and deriving what their complex representations are. Okay, so now it's time to start talking about transfer functions. So a transfer function is a function that describes the action of a circuit on an input voltage. It's a relationship between an input signal and the output signal, right? So let's say, let's illustrate this by example. And so let's say that we have this input voltage Vn is this sinusoidal signal with an amplitude V0, a frequency omega, and a phase theta. So we can use Euler's notation to express this guy as a sum of complex exponentials. So if we apply Euler's relation, remember the Euler's relation Euler's tells us that that e to the j omega times t is equal to cos of omega times t plus j times sine of omega times t. So then we can apply this relationship and arrive at the fact that Vn can be equivalently expressed as a sum of complex exponentials. Right? So this guy is a complex exponential, and we can express Vn as a sum of two complex exponentials. And what you get from that is minus j times V0 over 2 times e to the j omega t plus theta minus the complex conjugate of that, which is e to the minus j omega t minus theta. And so if you go backwards, as a sanity check, if you go backwards and apply Euler's identity to each of these two terms, then you'll see that the cosine component cancels out, and we end up with 2 times the sine component. Then the negatives cancel out, and you end up with this. Okay, so what you can see by having applied Euler's relationship here and expressing this as the sum of two complex exponentials is that this signal contains two frequencies. It contains a frequency of plus omega and a frequency of minus omega. So if you were to actually look at its spectrum, you would see that as a function of omega, if you look at its magnitude spectrum, so where the energy of this signal lies, so we can call this like the Fourier transform of Vn, the magnitude of the Fourier transform of Vn, you'd see that it has two spikes, one at the minus frequency and one at the positive frequency. So this would be minus omega, and this would be plus omega. Right. So if we express our transfer functions, our circuits, these equations that govern what our circuit does to input signals, as a function of frequency, for this particular signal, there are two frequencies we care about, right? There's a frequency plus omega and there's a frequency minus omega, and we basically need to evaluate our transfer function at those two frequencies, and then multiply it by our input signal, and then we get the output signal in the frequency domain. So, using circuit theory and impedance representations of elements, which we just introduced earlier, we can calculate the transfer functions for our circuits, which we usually write as h of j omega. And these functions are going to represent the effect of our circuits on input signals in the frequency domain. And in general, they're given by the ratio of the output voltage to the input voltage in the frequency domain. Right? So we can write this as the following: that h of j omega is going to be equal to the ratio of the output signal of j sorry, I'm having a hard time with the pen here, divided by Vn of j omega. The Fourier transform of each of these guys. So I'm writing that as the tilde on top of each of them. So one thing to note is that because each of these guys have units of volts, when you take their ratio, the units cancel out, so transfer functions are going to be unitless quantities. Another thing to note is that in this course, and in most cases, we're going to be dealing with conjugate symmetric transfer functions, meaning that meaning that the transfer function at a given positive frequency omega is equal to the complex conjugate of that transfer function at its negative frequency, right? So in the previous plot, we showed that a sinusoid has energy at both plus omega and minus omega. And so what this is saying is that we really only have to care about what happens on the plus omega side. So for real valued input signals, So this means that for real valued input signals, we only have to consider half, such as the positive half, of the frequency spectrum. So indeed, that's what we're going to do for the remainder of this lecture. And in most of your work, you only have to care about one half of the spectrum. So for our specific example of this input sinusoid function, the effect of a circuit with a given transfer function on this signal will be the following. In the time domain, we will get that V out is equal to V0 times the magnitude of the transfer function at this frequency omega times sine of omega t plus theta plus the phase angle, the phase shift introduced by the circuit, which is angle of j omega. Right, so here we have an amplitude shift, an amplitude change, which is this scalar in front, the magnitude of h of j omega, and our signal has also experienced a phase shift by this amount of angle of h of j omega. Okay, so the reason we go to all this trouble to represent circuits and the effects of circuits in the frequency domain is that we can now, armed with this knowledge about transfer functions and what they do to an input signal at given frequencies, we can now, armed with this knowledge, we can apply capacitors and inductors whose impedances change as a function of frequency to reject or retain signals based on their frequency. That is, we can design some arrangement of capacitors, inductors, and resistors to reject or retain signals based on their frequency content. So, for example, if you have noise in one part of your signal spectrum, of your overall spectrum of your input signal, but the signal you care about lives in a different part, then you can reject only the noise by designing an appropriate filter. So, for example, at some point soon we're going to be talking about having noise at 60 hertz, right? And you have signal maybe at 1 to 3 hertz. And so what you want to do is design a filter. What you'd like to do is suppress the noise without suppressing the signal. So you can imagine designing, using some arrangement of capacitors, resistors, and inductors, a filter that does not pass that has essentially zero h of j omega at the 60 hertz frequency, but is all ones over that 1 to 3 hertz range where the signal is that you actually care about. So to do this, remember that to actually build these things, we have to remember that capacitors have infinite impedance to DC. So DC is the frequency, is the zero frequency, right? And they have zero impedance to very high frequencies. If you recall, the impedance of a capacitor is equal to 1 over j omega c. So that guy is going to be infinite if omega is 0, because 1 over 0 is infinity, and it's going to be 0 if omega is infinity, right? So it's going to be a short circuit at very high frequencies and an open circuit at very low frequencies. On the other hand, inductors have zero impedance to DC and infinite impedance to very high frequencies. So you recall that that the impedance of an inductor is j omega L. So this guy is going to be 0 if omega is 0, and it's going to be infinite if omega is very high. Okay, so let's look at a specific example. Let's say that we have the following RC circuit. So we will have this input voltage that we're applying. We have a capacitor up top, a junction at which we extract our output signal. And then we have a resistor down here, and then it's tied to ground. Okay, and so then this is R, this is C, and this is going to be V out. Now we can equivalently represent this in impedances as the following circuit. We have V in again here, but then we have the impedance of the capacitor, Z sub C we'll call that. Then we extract V out up top, and we have Z sub R or just R, of the resistor. So you might recognize that when we look at this in terms of impedances, remember that impedances allow us to treat any circuit element like it's a resistor. So you might recognize that this circuit looks an awful lot like a voltage divider. It is a voltage divider, right? So we're looking at the proportional voltage across the resistive impedance, the resistor's impedance. So then that allows us to very quickly write out what the actual output voltage will be in terms of the input voltage. So V out then will be given by V in times R over R plus 1 over J omega C. This is what we get if we use the voltage divider equation with ZR over ZR plus ZC, and then just plug in the actual values of the impedances, right? And so this guy here is the transfer function, right? This is equal to J of omega, or H of J omega. This is H of J omega, this R divided by R plus 1 over J omega C. Okay, it is a function that relates the input voltage to the output voltage at a given frequency. Okay, so let's see what this guy actually does to input signals. So first let's say that Vin is a DC signal, so that omega is equal to 0. So we have to evaluate the transfer function. So to see what Vout is going to be, we have to evaluate the transfer function at this frequency 0. So then we know that Z sub C, the capacitor impedance, is going to be infinite, right? So if that's infinite, then that's like we have an open circuit. We've broken the circuit there, so we know that no current is going to flow through that. And so V out is also going to be 0, because if there's no current going across ZR, then you have that V out is equal to the ground, right? This has to be at the same potential as the ground if there's no current flow. So this result is independent of the sizes of Vn, R, and C, right? If we turn up Vn to 100 volts or 1,000 volts, we're still going to get no output voltage because this is an open circuit, so no current is flowing. Okay, so let's think about the opposite situation. What happens if the frequency omega is very high? So let's see what happens if omega is infinity. At this frequency, we're going to have that the capacitor's impedance is going to be 0, right? Because 1 over infinity is 0. So we get a short circuit there. So the capacitor just goes away. It's replaced by a short. And so now all of the voltage drops across the resistor, and so then the current is equal to Vn divided by the resistor, the impedance of the resistor, which is R, and V out is going to be equal to Vn. So it does nothing. It does so nothing happens to the input signal. It completely passes it. Whereas in the previous case with the DC signal, that signal was completely completely suppressed by the circuit. If we look at some point, in between, say omega is 100, right? So let's say that omega is 100. Let's say that R is 1 kilo ohm and C is 1 microfarad. Then now we have that this frequency is 100, and that we can actually calculate out what the impedance is of the capacitor at this frequency, and we can plug that in and get the transfer function at this frequency. Note that it has both a real part and an imaginary part. I'm sorry, there should be a parentheses here. Right, so it's got both. So it's going to be the ratio of these two values, and it's going to have real and imaginary parts to it. And if you note that the magnitude here, so if you look at if you actually calculate what the magnitude of this guy is, then we get 10 to the third divided by square root of 10 to the third plus, 10 to the third squared, which is 10 to the sixth, right? Plus 10 to the fourth squared, 10 to the 4th squared, which is 10 to the 8th, right? So if you get right, so anyways, if you sum these two numbers together, you can see right away that this number is going to be you can see right away that the denominator is going to be bigger than the numerator, right? Because you're adding two numbers that are positive together, right? And one of them is the numerator value. So this is going to be bigger than the numerator, so it's going to be attenuated somewhat at this frequency. The signal will be attenuated somewhat. So this is somewhere in between DC and infinity. Okay, and now we can actually, if we were to actually plot the magnitude of h of j omega for a range of omega values, we would get something like the following. So note that here I'm going to be doing a log-log plot. So both variables, I'm taking both the logarithm of omega, and I'm taking the logarithm, and I'm taking the logarithm of magnitude of h of j omega. If we plot these against each other, we see that we get these sort of three zones. We have a rise up, and then we have sort of a corner there, and then it goes flat. So then we can kind of define these three zones, right? We can define the zone, we'll call this guy zone 1, call the middle part and the transition zone 2, and the flat part at the top zone 3. Okay? So earlier we saw that this filter does not pass DC, so then the magnitude of h of j omega at DC at 0 frequency is going to be extremely small. That's going to be 0, and then we have some transition zone where things are attenuated somewhat, but not quite, not fully passed. And then we have the very high frequency zone, that's zone 3, where things are fully passed, right? So this filter is called a high pass filter then, right? Because it suppresses low frequencies and passes high frequencies. It suppresses low frequencies and passes high frequencies. And so it has these three distinct zones. Zone 1 is where you are doing the suppression, and in this zone the impedance of the capacitor is much bigger than the resistor, right? So the impedance of the capacitor is very big, it's stopping current flow, and it's much bigger than the resistor. In zone 2 we have this sort of elbow region, and that's where the impedance of the capacitor is roughly the same size of the resistor, or equivalently the real part of the transfer function at these frequencies is approximately equal to the imaginary part of the transfer function at these frequencies, or they're at least maybe on the same order of magnitude. And then in zone 3 we have that the impedance of the impedance of the capacitor is very small compared to the impedance of the resistor, so it's acting more and more like a short, especially as we increase frequencies really high. So one other thing I'd like to say about this, having note about this, is that you can see that zone 1 on this log-log plot looks very linear, right? And you can actually see that from the transfer function of this circuit. Right, so if you recall that the transfer function is has the form r over r plus 1 over j omega, 1 over j omega times c, then for very small omega, remember that the capacitance for very small omegas, we have that the impedance of the capacitor is much bigger than that of the resistor, so you can pretty much neglect the resistor term in the denominator, and so for small frequencies we get that this is approximately equal to r divided by 1 over j omega c, right? Which is equal to j omega rc. And so if we plot this, we can see that now the transfer function magnitude is approximately excuse me, the transfer function magnitude is approximately proportional to omega. So if we plot the magnitude versus the log magnitude versus the log omega, we get a line, right? And so that's why we see that there. Okay, so in zone 1 we have that's like the stop band, that's where the signals are suppressed. And in zone 2 we have the point where the real and imaginary parts are about equal in size, and that's where we have this rounding off, right? So we had on the previous slide I showed the plot where the transfer function goes like this. So zone 2 is this area. And we have in that area we have this elbow, right, where it transitions from where the transfer function amplitude transitions from this linear regime to this slant regime on a log-log plot. And that point where the real and imaginary parts are about equal in size is called the corner, or the cutoff, or the break frequency. So this can be expressed in hertz as f sub c, or in radians per second as omega sub c. But it's this point where we have the corner, right, of the where we have the corner of the transfer function amplitude. And in this place, in this area, in this region, we have that the real and imaginary parts are about equal. So here we have that A over A plus A sub j. This is the form of our transfer function approximately at this corner frequency. We have that the amplitude of this guy is equal to square root of a squared divided by square root of a squared plus a squared, right? So 2a squared, which is just equal to a over a times square root of 2, which of course is just equal to 1 over root 2, or 0.707. Remember that familiar number. And so you recall also that 20 log of 0.707, or 1 over root 2, is minus 3 dB. So this omega sub c or f sub c, this is the 3 dB down point of the filter, right? This is what we call the corner frequency, and it is also the 3 dB down point, the point at which the input signal is depressed by minus 3 dB compared to the maximum output you can get. Okay, so we just looked at a filter that has we just looked at a high-pass filter. So let's see what happens if we simply swap the places of the resistor and the capacitor. So now we have the input voltage here still, but now the resistor is up top. We pull the voltage out there, and now we're measuring the output voltage across the impedance of the capacitor instead of across the resistor. And this is going to see, we're going to see that doing this changes the behavior of the circuit entirely. So again, we're going to say that we have this R here and C here, and so then we have V out here that we're taking across, measuring across the capacitor. So H of j omega, the transfer function, is going to be equal to Z sub C divided by R plus Z sub C. If we plug in 1 over j omega c for Z sub c, and we multiply top and bottom by j omega c over j omega c, then we arrive at 1 over 1 plus j omega times R times C, right? And if we plot this guy's transfer function, we are going to see that it is a low-pass filter now. So here we have the flat region, then a corner, and then a linear drop-off on a log-log plot. So here's log omega and log of magnitude h of j omega. Right, so this is going to be, now we've got these three zones. In the zone 2 is again contains the corner frequency. So this is about the right here is the 3 dB down. Okay? And so this guy is a low-pass filter, and we've gotten a low-pass filter just by swapping the places of the resistor and the capacitor. And you can see that it's going to be low-pass just by looking at the form of the transfer function as well, right? Because if you have omega is equal to 0, that's DC, so that's the low end of the spectrum, then this term is going to vanish, and we're going to get just 1 over 1. So it's going to just pass those signals at those frequencies. Whereas if omega becomes very big at the very high frequencies, when omega is very big, then this term dominates the 1 there, and we get just 1 over j omega RC, which is, as omega increases, is going to go to 0. So this is a low-pass filter then. Okay, so that concludes this lecture. So here we talked about the following 4 topics. We talked about the impedances, the impedance representations of basic circuit elements. Resistors have an impedance just equal to their resistance, R. Capacitors have impedance 1 over j omega C, and inductors have impedance j omega L. So in the capacitor and inductor impedances, j is the square root of minus 1, and omega is the temporal frequency of the signal. And then C or L is the capacitance in farads, or the inductance in henries. We gave a review of complex arithmetic, how we can multiply, how we can divide. We defined complex numbers again as some real part A plus some imaginary part B. So then, if you have the two of them, you can construct a complex number A plus BJ. And we also then transitioned into thinking about the frequency domain thinking about the effects of our circuits in the frequency domain, which led us to think about transfer functions, so frequency-dependent transfer functions that relate an output signal from a circuit to its input signal. And we talked about passive, high, and low-pass filters. So again, passive filters are those which contain only resistances, capacitors, and inductances. And we first gave an example of a high-pass filter, and then we gave an example of a low-pass passive filter. So that's it. Thanks.